Supplemental math videos from Circle Christian School. Complex numbers, living in an imaginary world. Complex numbers are used for many different things. One of them that's most prevalent is for the impedance of an electrical circuit. You'll see them in sound, basically anything that you really have in the real world that you can't see but does have an effect on you. Oops, I forgot to zap you. There you go. You've been zapped. Complex numbers came about when mathematicians knew that there were things like negative radicals, but they really didn't know what to do with them. And it wasn't until much later that a famous mathematician he actually discovered this while he was on a walk, and just happened to be looking at a plaque and went kind of like, eureka, I think I know what to do with them. He started treating them like real numbers, the real number system, but it was for, you guessed it, imaginary numbers, the complex number. So basically the square root of -1 equals the square root of 1i. It's imaginary. And if you have I squared, the big things that you need to know if you have I squared is that it always equals -1, because the square root of -1 times the square root of -1, any radical times itself always equals itself, therefore it equals -1. Kind of crazy, but it works. So we can actually add and subtract them. You just treat them like terms, a constant number to a constant number, the imaginary number to the imaginary number. So for instance here, we would just take the 3, add it to the 8, and we would get the 11. And then -i plus the 3i here would just give you a +2 and an I. Adding and subtracting, pretty cool. The only thing you have to remember in the subtracting is that the negative basically gets distributed out here. But if we keep to the like terms thing, constant number to a constant number, a imaginary number to imaginary number, it's not that hard to bring out into the work. 6 minus the 4, jumping around there, it's going to give you a 2. And then a -2i minus the 8i gives me the -10i. So that's just kind of like terms. And of course we can multiply them. You just have to remember the number to number, letter to letter thing. Just covered up by 4 there. So I would just go 4 times the -1 would equal a -4, and of course it has an I. And then a -4 times a +5 would give me a +20, and then we would have I squared. Remembering that I squared actually equals -1, so we can actually replace that with a -1, our final answer would be -4i, and then 20 times the -1, or -20. And generally we like to write these as real number first, our imaginary number second. So it would be a -20 minus the 4i. The foiling rules work when you have a binomial times a binomial. And again, what plays here is the number to number and the letter to letter thing. So we're going to have 3 times the 4 is the 12. 3 times the 2i is a 6i. Going to do the other guy, make sure that you include the sign there. So a -2i and the 4 is a -8i. And then a -2 times the 2 is going to give me a -2, but the I times the I is going to give me the -1. You can go ahead and put that down. You don't even have to do it as an I squared. And then we're just going to combine our like terms. That's what foiling is all about anyway, distribute and combine like terms. And you can start with the I things. So we have a -2i. And then we have the 12 and the +2. So plus a 14. Oops, I did that backwards. I don't know why I did the i's first. Oh, well. I'll let you change it, and that'd be kind of a cool thing that you go, ah, Mrs. Washington did it backwards. And then we have the binomial square, same rules. With a binomial square, try to get quick. This is somewhat of a 5-second one. It's going to be the first number squared, so that is 64. And then it's going to be the guys inside here twice, so 8 times a negative 2 is negative 16 twice, so a negative 32i. And then we're going to square the last guy. A negative times a negative is going to give us a positive. Square of a 2 is a 4. The square of an I is a negative 1. And let's see if I can do it proper. We have negative 4, 64 should be a 60. And then a negative 32i. And gee, if we can add, subtract, and multiply, it would just only stand to reason that we can also divide these. But I'm going to start with the difference of two squares here to see what kind of happens with them. And with the difference of two squares, it's always the first guy squared, so that's going to be a 36. And we're going to have the second guy squared, which is going to be a 25i squared, so the negative 1. And it's a minus sign in between, and we notice, hey, it now becomes this cool little positive number, 36 plus the 25, so we get a 61. And it gives us a real number. We call this conjugating the complex number by using the difference of two squares here. So we're going to do the same thing with this one that we have as the division here. Let me erase everything. So I'm going to conjugate the denominator here because I need to make it real. You can't have imaginary pizza slices anyway because that's what the denominator is. I'm going to go 1 minus the 4i. And anything that you do to the bottom, the denominator, you must also do to the numerator. So the 1 minus the 4i. Now the bottom part's probably the easiest to do first. So we get the 1 squared, which is going to give us 1. We get the 4 squared, which is going to give us the 16. And we know that it's always going to end up being a positive number. So we have the 17. And now we're going to do the top part. We'll have to do the foiling out. So we have the 2 times the 1, which is 2 times the negative 4, negative 8i. Then the 3 times the 1, so negative 3i. And the negative 3 times the 4 is a negative 12. And then the I squared. Oops, maybe I should move them out a little bit. That's all right. We'll just rewrite it. We get the 17 there. And so we have a 2 plus a 12. So we have a 14. And then we're going to do the i's. So negative 11i. And what you have to watch out for here is that the denominator of 17 actually has to be split off because we have real number here and then we have the imaginary number over here. So standard form dictates that you actually have to separate it out like so, and that's going to allow you to simplify anything as needed. Remember, all fractions need to be simplified. Next, the reason why we do this is because sometimes we get this negative radical while working in the quadratic formula. So the first thing I like to do is identify my A, B, and C's. So I have a 3, negative 2, and a positive 5. I like to build a template for my quadratic formula, so that way I can just place things in. I do my quadratic formula just a tad different. You may have it where it's all over 2a. I like to separate it out because that makes the simplifying a little bit easier. And again, if you get anything complex, the real's already separated from the imaginary if that's what happens. So Let's see, I got a 3 here and a 3 here. We're going to put in the b's, the -2, -2, building a template with the little parentheses, keeps all the little integers happy. And then we're just going to do the work. I'm going to start with the real part first, and that's going to give me a 2/6, which we know is 1/3. Very good, plus minus. See, I was able to actually simplify that as needed. And now we're going to do the next guy, so that's going to be a 4 minus 12 times 5 is 60 over the 6. We know that's going to equal a -56. So we end up with a square root 56i over the 6. And of course, the one thing that you have to remember about radicals is that you always have to simplify. When you think you're done, you have to simplify some more. So you're going to have to simplify the little radical here, whichever way you like. I like doing the prime number thing, prime factorization, so whatever works for you. So 56 is 8 and 7. So 7's a cool little prime guy. 8 is 2, 2, and 2. So I know I can take a 2 out and a 14 is going to stay inside. So a 2 comes out, the 14 stays inside. Got the little I going on over the 6. So we can simplify that. So that's 1/3. Generally, these things should always be pretty much the same. Not always, but they should be somewhat pretty much the same. And so you end up with 1/3 plus minus square root 14i all over 3. And now you're a quadratic, very complex person. Have an awesome day.